Hello everyone and welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 1.1 from the October-November exam period of 2020. So let's get straight into it. In exercise 1 we are provided with a diagram that shows the graph of y equals the absolute values of the function p, whereby p of x is a cubic function. We are supposed to find two possible expressions for this function. In order to do that, we are going to determine the intersections of the function with the x and y axis. At first glance we can see that the 0 points of the graphs are located at x equals -2, -1 and +4. We can exploit this information to make use of the factors of a polynomial, which you can see at the right hand side of the screen. From there we can derive that x plus 2 multiplied x plus 1 multiplied x -4 equals 0. For the aforementioned 0 points of -2, -1 and +4. Additionally, we know that for x equals 0, our y value equals 24. What we need to figure out now is our coefficient a. For that we simply replace all of the x's in the brackets with 0, which leaves us with this equation over here, and rearranging it for a delivers us the result that a equals -3. Since, as per the exercise, y equals the absolute value of the function p, the value for a can either be positive or negative. Thus our two possible expressions for p of x are plus or -3 multiplied x plus 2 multiplied x plus 1 multiplied x minus 4. Moving on to exercise 2, in part A we are supposed to write down the amplitude of 1 plus 4 cosine x over 3. The amplitude is determined by the factor that is in front of the trigonometric function, which in this case is 4. We can this also call the coefficient of our trigonometric function. For more on that, please take a closer look at the information provided to the right on your screen concerning the amplitude, period and phase shifts of trigonometric functions. In part B, we are supposed to calculate the period of the expression 1 plus 4 cosine x over 3. The standard length of a period equates to 2 pi, thus we equate x over 3 to exactly that number. Rearranging this equation provides us with the length of the period, which equals to 6 pi. In C, we are supposed to sketch the graph of y equals 1 plus 4 cosine x over 3 within the interval of -180 and +180 degrees. To do that, we can take advantage of the information provided to the right of your screen and rewrite our function accordingly. From here we should be able to see that our amplitude is 4, our period length 1 over 3, and that the vertical shift equates to +1. This means that our cosine function is point symmetrical to y equals 1, and as our amplitude is 4, we would have to move 4 units up in order to determine our maximum point within this interval. In order to find the value of this function for x equals -180 and +180 degrees, we need to keep in mind that 180 degrees equals pi. Substituting pi and -pi for x in our function will provide us with the value of +3. From there, moving on to exercise 3a, here we are provided with the following expression, which we are supposed to rewrite in the form p to the power of a, q to the power of b and r to the power of c, where a, b and c are constants. To achieve that, we will make use of the laws of exponents for fractional exponents, which you will find to the right hand side of your screen. This law states that the square root of p can be transformed into p to the power of 1 over 2. Furthermore, for the expressions q r squared to the power of 1 over 3 and q cubed multiplied p to the power of -1, we will make use of the power rule of the laws of exponents, which you can also find to the right hand side of the screen. Combining these two laws will deliver us the expression over here. From there we will transform the denominator into a multiplication by changing the signs of the powers in our denominator. So q -3 turns into q cubed, p to the power of -1 into p, and so on. In a final stage we simply add up all of our exponents in order to simplify our expression, which brings us to the simplified result of p to the power of 3 over 2, q to the power of 10 over 3, and r to the power of -7 over 3. In part B of exercise 3, we are supposed to solve the expression 6x to the power of 2 over 3 minus 5x to the power of 1 over 3 plus 1 equals 0. This can be achieved in applying Vieta's formulas, which you can find to the right-hand side of the screen. To figure out whether or not this rule can be employed here, we need to closely inspect the power expressions x to the power of 2 over 3 and x to the power of 1 over 3 and realize that x to the power of 2 over 3 equals x to the power of 1 over 3 squared. So what we could also do is to work with substitutions. So we could say that x to the power of 1 over 3 could be substituted with u. From there we would receive the expression 6u squared minus 5u plus 1 equals 0. And from there it should be pretty clear that Vieta's formulas can be employed in order to solve this equation. Moving on to exercise 4, where y equals tangent 3x over sine x is given. In part A, we are supposed to find the exact value of dy over dx when x equals pi over 3. To achieve that, we need to find the derivative of this expression and then substitute x for pi over 3. Since the expression tangent 3x over sine x is a fraction, we will employ the quotient rule for derivatives, which you will find to the right-hand side of your screen. In which case u will be tangent 3x and v sine x. After substituting pi over 3 for x, we simply need to put all of those expressions into our pocket calculators. And after simplifying all of that, we should come to the result that the exact value for the expression y equals tangent 3x over sine x equals 2 multiplied the square root of 3. In part B, we are supposed to find the approximate change in y as x increases from pi over 3 to pi over 3 plus h, where h is small. To do that, we simply expand from our previous result in part A of exercise 4 and multiply this with h. Part C expands further on that. Here it is given that x is increasing at the rate of 3 units per second, and we are supposed to find the corresponding rate of change in y when x equals pi over 3, and we are supposed to provide our answer in its simplest third form. So what we need to do here, we will take a look at our result of exercise 4b and replace h, which corresponds to the increasing rate, with 3. And as 2 multiplied 3 equals 6, our final result for that exercise would be 6 multiplied the square root of 3. Next on to exercise 5. In part A1, we are supposed to find out how many different 4-digit numbers we can form using the digits 1, 3, 4, 6, 7 and 9. Each digit may be used once only in any 4-digit number. Our key phrase here is may be used once. So in the first place, we can choose freely from all of those 6 numbers here. In the second step, our options are reduced by 1 digit, leaving us with 5. In the second step, we are only left with 4 options. And finally, for our last digit, 3 of those have already been used up, leaving us with 3 to choose from. Multiplying all of those numbers will lead us to the conclusion that there are 360 different 4-digit numbers which can be formed using those 6 digits mentioned in the exercise. In the second part of exercise 5a, we are asked to find out how many of these 4-digit numbers are even or greater than 6,000. So in the first step, it should become clear to us that our first digit must be either 6, 7 or 9, as our numbers are supposed to be at least 6,000. So when we are to start with 6, our final digit must be 4, as our numbers are also supposed to be even, and 4 is the only even number that is given in the exercise. So after the digits 6 and 4 are used, we are only left with 4 more digits to choose from, which means that for the second digit we are provided with 4 options, and after reducing our pool of options with 1 digit, from there we are just left with 3 more digits to pick from, and 4 multiplied 3 equals 12. So we have 12 options for 4-digit numbers that are even and between 6,000 and 6,999 inclusive. From there we need to take a look at our 4-digit numbers that start with 7. In this case, our last digits can either be 4 or 6, since 4 and 6 are even numbers. Since 7 in the first place is given and the last digit can either be 4 or 6, which are 2 options total, we should be able to derive from there that there are a total of 4 multiplied 3 multiplied 2 options for 4-digit numbers that start with 7. If our 4-digit number were to start with 9 instead of 7, everything else would be the same except for the leading number. So in this case as well, we would be provided with 4 multiplied 3 multiplied 2 options, which are 24. For 4-digit numbers would have 9 as their leading number. So at the end, we simply need to add up our options for 4-digit numbers starting with 6, 7 and 9, which will get us the result that there are 60 numbers that are even and larger than 6,000 that can be generated under the given constraints. Next, on to part B of this exercise. Here it states that there is a committee of 5 people that is to be formed from 6 doctors, 4 dentists and 3 nurses. We are supposed to find the number of different committees that could be formed if in B1 there are no restrictions. So when it comes to forming a committee, the order by which kind of person the committee is formed does not matter, which means that we are dealing with a combination. Since each person can only be part of the committee once, we are dealing with a combination without repetition, which formula you can find to the right-hand side of your screen. And after putting all of these numbers accordingly into a pocket calculator, we should come to the conclusion that there are 1,287 possible combinations of forming a committee of 5 people from a total of 13. In the second section of part B, it is stated that the committee contains at least 1 doctor, which means that we need to subtract all of our combinations where there are no doctors on the committee from all of the options available to form it. There are 7 persons in total who are not doctors, and after employing previously shown formula, we should conclude that there are 792 ways to form a committee with at least 1 doctor under the given circumstances. In the final part of exercise C, we are supposed to form a committee that contains all the nurses. The total number of nurses is 3, which means that there are only 2 positions in the committee left for the remaining 10 people, which consists of 6 doctors and 4 dentists. The solution for this combination is 45. Over to exercise 6, where a particle P is initially at the point with the position vector 30, 10 and moves with a constant speed of 10 meters per second in the same direction as -4, 3. In part A, we are supposed to find the position vector of P after t seconds. To do that, we first need to determine how far our particle P has traveled, which we kind of know. It states here 10 meters per second. What we need to do is to translate it into a fitting direction vector. To achieve that, we will determine the length of this vector using the formula to calculate its magnitude provided to the right-hand side of your screen. After applying this formula, we are coming to the conclusion that the length of this direction vector is 5. From there, we can see that the length of this direction vector represents half the distance that the particle traveled in 1 second, so we need to multiply it by 2, since 10 divided 5 equals 2. Once we determined the result for this direction vector that fits our situation, we come to the conclusion that the position of the vector P after t seconds is 30, 10 plus -8, 6 multiplied t. Leading to part B, we are provided with the information that as P starts moving, a particle Q starts to move such that its position vector after t seconds is given by the expression -80, 90 plus t multiplied 5, 12. We are supposed to write down the speed of Q. To determine the speed of this particle, we need to calculate the length of the directional vector in order to determine the particle's speed. Again, we simply need to employ the formula that helps us in calculating the magnitude of a vector for the directional vector, after which we come to the conclusion that the particle Q travels at the speed of 13 meters per second. In part C of exercise 6, we should find the exact distance between P and Q when t equals 10, and we're supposed to give our answer in its simplest third form. What we first need to do is to find both of those particles' positions after 10 seconds. To do that, we simply substitute t for both particles with 10. And in a second step thereafter, we determine the distance between the particles P and Q after they have reached their final destinations. To do that, we subtract their final positions, and as previously, in order to determine the distance, we just calculate the magnitude of this vector, after which we can conclude that the distance between P and Q equals 100 multiplied the square root of 2. Moving on to exercise 7, it is given that the function f of x equals 5 multiplied the natural logarithm of 2x plus 3 for the values of x larger than -3/2. We are supposed to write down the range of the function. Since the expression within the parentheses can never be negative due to the constraints that x is required to be larger than -3/2, the range for this entire expression will thus be all of the real numbers. In part B, we're supposed to find the inverse of this function and state its domain. We can achieve that by rearranging the function for x. In the first step, we will divide this equation by 5. In the second step, we make use of the relationship between natural logarithms and natural exponential equations, which you can find provided to the right-hand side of your screens. Continuing from there, we will isolate our x expression, which is 2x, whereafter we will divide it by 2 in order to fully isolate x. Lastly, we will substitute y for x and come to the conclusion that the inverse function is e to the power of x over 5 minus 3 over 2. As there are no restrictions to the power of an e function, its domain are all of the real numbers. In part C of this exercise, we are supposed to sketch the graph of f of x and its inverse. We are supposed to label each curve and state the intercepts on the coordinate axis. To receive the y-intercept and our 0 point for the given function, we substitute x for 0 in the function in order to receive our y-intercept, for which the value is 5.5. Similarly, for the intercept with the x-axis, we set the function for 0, and doing that with the help of our pocket calculator, we arrive to the conclusion that this value is -1. Since the property of any inverse function is that it mirrors its original function to the line of the first meridian, which is this line here, it can also be represented by the function y equals x. So from there, we know that the inverse function intercepts the y-axis at -1 and the x-axis at 5.5. Continuing with exercise 8, in A part 1, we should show that this expression is correct. To achieve that, we need to ensure that the expression of 1 plus cosecant theta is transformed to an expression that contains sine theta. This can be achieved by taking a closer look at the trigonometric identities which are provided with to the right-hand side of the screen. One of which states that the expression cosecant theta equals 1 over sine theta. From there, we will simply expand the expression of the product in the denominator. After simplifying this expression gradually, we come to the expression 1 over 1 minus sine squared theta, and again applying the trigonometric identities which I will provide you with again on to the right hand side of the screen, we should see that this expression 1 minus sine squared theta equals cosine squared theta, which in return equals secant squared theta, which was to be shown. The second part of exercise 8a requires from us to solve this equation for the interval of theta between -180 and +180 degrees. Similarly to the first part of exercise 8a, we will replace this expression for 1 over sine theta according to the trigonometric identities. Thereafter, we are expanding those two factors here, simplify those, and replace the expression 1 minus sine squared theta according to the trigonometric identities using Pythagoras theorem, which is provided to the right hand side of the screen. From here, we simply need to find the root for this expression, which provides us with two solutions. From there, we can convert our results back into the angles that we are looking for, which are -150, -30, +30, and +150 degrees. Continuing with part B of exercise 8, here we are supposed to solve this equation for the interval between 0 and 2 pi over 3 radians. We are required to provide our answers in terms of pi. We should realize that both of the expressions within the parentheses are the same, and exploiting our knowledge of trigonometric identities, which you can find to the right hand side of the screen, we should know that we can convert this expression into tangent equals 1. Additionally, we should know that tangent x equals 1 is true for all x's that equal pi over 4 plus pi multiplied n being an element of the whole numbers. Therefore, the following equations need to be solved until all solutions within the requested interval, which we can find on top, are found. So in the first step, we equal the expression within the parentheses with pi over 4, which we get if we were to set 0 for n. Simplifying this equation delivers us a result that is less than 0, which is not within the interval. Thus, this is not a result that we are looking for. Continuing from here, since our first result has been negative, we will continue with replacing n for natural numbers, since we would otherwise continue to be receiving negative results, which are not within the interval that we are looking into. So pi over 4 plus pi equals 5 pi over 4. Rearranging this equation for phi delivers us a result that happens to be within the constraints of our interval. Next, we will again increase n by 1. So pi over 4 plus 2 pi equals 9 pi over 4. We will again rearrange this equation for phi and receive again a result that is within the constraints of our interval. We will continue this process until we receive a result that is larger than 2 pi over 3, which happens on the next occasion. Replacing n with 3 will deliver us the expression pi over 4 plus 3 pi, which equals 13 pi over 4. Rearranging this expression for phi delivers us 31 pi over 36, which is larger than 2 pi over 3. Meaning that this equation is fulfilled for phi equals 7 pi over 36 and 19 pi over 36. On to exercise 9a, where we are dealing with this expression where a is larger than 0. Furthermore, we should give our answer in its simplest third form. So in the first step, we will expand the integration using the difference rule, which you can find to the right of your screen. In the second step, we will substitute the integrand 1 over 2x plus 3, whereby the denominator will be substituted for u and du equals 2 dx, since the derivative of 2x equals 2. From there, we can employ the reciprocal rule for integrations in order to integrate both of those expressions. Once we arrived here, we can resubstitute u for 2x plus 3 and expand those expressions. When expanding negative 1 over 2 multiplied by the natural logarithm of 2a plus 3 minus the natural logarithm of 5, we need to keep in mind that all of the signs within the parentheses need to be changed due to the fact that we are multiplying everything with a negative number, in this case negative 1 over 2. Since the coefficients of the second and the third summand are 1 over 2, using the basic laws of logarithm, we can transform the expression ln a into the expression 1 over 2 ln a squared, which will help us in factorizing 1 over 2 for all of those summands. Again, using the basic laws of logarithms, which you will be provided with to the right hand side of the screen, we are able to transform this expression into this fraction here. And using the same rules, we can transform this factor into this power. Since the expressions to both sides of the equation relate to the natural logarithm, we simply need to compare the expressions to the corresponding right hand side. From there, we square both sides of the equation and rearrange it for a quadratic function. With the help of the quadratic function rule, which you are provided with to the right hand side of the screen, we will receive those two results. The negative 1 would be void since it is not larger than 0. Thus, our final solution in the simplest third form is 9 plus 6 multiplied the square root of 6 over 5. Part B of exercise 9 requires from us to find the exact value for the following expression. To To achieve that, we firstly need to find the right integration for the expression within the parentheses, which is achieved through a combination of the integration of trigonometric functions and the power rule, which we're provided with to the right-hand side of the screen. From there, we simply replace x for their boundaries pi over 3 and 0 and simplify our expression accordingly. Please be mindful when simplifying this latter part of the expression. Since we have a negative sign in front of the parentheses, all of the signs within need to be reversed. Additionally, the sign of 0 equals 0, this is why it can be dropped. With the help of our pocket calculators, we can simplify all of our trigonometric expressions. Simplify our expression further until we receive the exact value. The exact value would not be the rounded result that your pocket calculator might provide you with, as we are requested to deliver the exact value, and a rounded result is never exact. Thus, our result here is 3 over 4 plus the square root of 3 over 4 minus pi over 3. We have reached the final exercise of this exam paper, exercise 10. In part A, it is mentioned that an arithmetic progression has a second term of 8 and a fourth term of 18. We are supposed to find the least number of terms for which the sum of this progression is greater than 1560. Our key phrase is here arithmetic progression, and you're provided with the arithmetic sequence rule to the right-hand side of your screen. The exercise states that the second term is 8 and the fourth 18. According to the previously mentioned rule, we know that a plus d equals 8, since a, our first term, plus the common difference provides us with the second term. Furthermore, a plus 3d must then equal 18, since the first term plus 3 times the common difference equals the fourth term of this arithmetic progression. We will now use this system of equations in order to determine first term of the progression a1 as well as the common difference d. Firstly, we take this equation and rearrange it for a. We will use this then to substitute d for a in the second equation. From there, we just separate the d's from the numbers, isolate d, and receive our results, which are 3 for the first term of the arithmetic progression and 5 for the common difference. Furthermore, we are supposed to find the least number of terms for which the sum of this progression is greater than 1560, which can be done using the sum rule formula provided to the right-hand side of your screen. So we simply replace a for 3 and 5 for d and set up the inequality accordingly, meaning that the sum should be larger than 1560 as stated in the exercise. In step 1, we expand and simplify the expression within the parentheses. In the second step, we multiply the equation with 2 and expand the expression n multiplied 5 plus 5n at the same time. Afterwards, we arrange it in a way that we receive a quadratic formula, which can be solved according to the information that you can find to the right-hand side of the screen. The formula will provide us with two potential results, of which only the positive one can be correct, since n represents the natural numbers. Finally, we need to round up 24.48, since we are required to find the least number of terms for which the sum of this progression is greater than 1560. For 24 it would just be below, for 25 it will certainly be greater than that. Coming to part B of exercise 10, a geometric progression has a sum to infinity of 72. The sum of the first 3 terms of this progression is 333 over 8. Part 1, we are supposed to find the value of the common ratio. The key phrase of this exercise is geometric progression. And to your right, you will be provided with the sum rule for geometric progressions. So to find the value of the common ratio, we can firstly employ the first part of the statement of this part of the exercise, which states that this geometric progression has a sum to infinity of 72. And we can employ this piece of information to rearrange this expression for a. In the second step, using the formula to determine the sum of a geometric progression, we can use the second part of the statement saying that the sum of the first 3 terms of the progression, S3, equals 333 over 8. What we can now do is we can substitute a for the expression 72 multiplied 1 minus r, and in doing so we just need to determine the value of r. In step 1 we will employ the means of cross-multiplying this equation of fractions to get rid of the denominators. Secondly, we will expand both sides of the equation and rearrange it for a cubic function. From here, since all of the digits of those numbers add up to a multiple of 9, we can simply factor this expression by 9, divide the entire equation by the very same number, and from here we can simply use our pocket calculators in order to determine our value for r, which is 0.75. In part 2 of exercise 10b, we are supposed to find the value for the first term. For this we can simply use our expression from exercise 10b1, which states that a equals 72 multiplied 1 minus r. We replace r for 0.75 and come to the conclusion that the first value of this geometric progression is 18. I've been your host Marco from Planet Maths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers!